Hello, and welcome to my presentation of the Geologic History of Earth and Antarctica. I will be using a series of photos, and I tried to get them in the best order that I could, but there's a lot of things that are interconnecting, so it's hard to lay them out right in a row. So some of them may seem out of order, but like I said, everything interconnects. So in order to cover the geology of the Earth, we have to go back at least 4.6 billion years, if not farther. Earth was formed around into what you see here about 4.5 billion years ago. Now, the cloud of dust and debris that the solar system formed from actually started to coalesce pretty well about 5 billion years ago. So it took apparently 500 million years for it to get to this point. This is the planet itself. Of course, it wasn't quite this serene. There was a lot of debris still around. I think the planet had rings around it, as does Jupiter and Saturn have rings. Uranus also, I think. So we have rings all over. Why not Earth? And it's also being pummeled constantly with debris, asteroids, comets, whatever, at this point, where they do break the surface and it just makes a big splash. These, if they're large enough, they'll actually go into the interior, into the magma, and be melted. Now, the Earth's atmosphere really didn't form 4.6 billion years ago. It started to form 4.6 billion years ago. And, of course, the theory here is, at first, of course, it did not have an atmosphere or free water, since the planet was too hot for gases and water to collect. The atmosphere and oceans that we see today evolved over time. The gases came from within the planet and from far out in the solar system. Okay, so they're saying basically here that the water came from outer space, I guess in icy comets or asteroids. And when I say the Earth was pummeled, you have to imagine how many it took to fill the oceans of the Earth right now. And also there was a lot of degassing, of course, just like a volcano. You get the carbon dioxides and all kinds of gases forming because the magma is made up of elements and minerals, and gases are elements, and they will combine. You have hydrogen, oxygen. Our atmosphere is mostly nitrogen. Anyway, they will combine to make steam or water vapor or air. But if right at first, it is obviously too hot for that. Here's another picture that shows the same scene. One thing to mention here is there was the intense cosmic radiation. Because there's no atmosphere, you're getting the full blast. So kind of stands to reason that you don't have microscopic organisms or plants growing even on the land that does form right at first, because if that also includes all of the UV and well, everything but UVC, which would probably kill any microorganisms that might be trying to form. So really it wasn't a good environment for life to form yet. So here we have the Earth showing it's got its water now. The moon is formed. This is claimed to be about 4.6 billion years, but I think it's probably more closer to 4 billion. Not sure if the Earth would have these open gashes in it like that with the water, up here. It doesn't really show if that's on land or not. Maybe they're showing two stages here. I don't know, but this is an awful lot of water by now. You can imagine how many comets had to hit Earth to get that. I think at this point we're still being barraged here pretty well, even though the picture doesn't show it. But and also the moon. We'll talk more about that moon. This is more realistic here, except that I think there would probably be more rings than not. But this is a good depiction of the debris that's all over the place. All of these boulders or asteroids formed supposedly from dust that collected together, and they just got bigger and bigger, and just from this attraction of the dust. Now here's the one theory about the moon being formed, and they're saying 4.5 billion. Of course, nobody knows any of this for sure. If you look at this, and I don't really agree with this at all, but look at this first picture here. They're saying a planet-sized object struck Earth. Well, it must have been pretty big. And then in the middle we have this miraculous ring formed here out of the blast that went, looks like 360. Seems a little early. I guess we probably had magnetic fields here, because the magnetic fields is what you have to have here to get things rotating around, possibly as rings. This is a ring, but it's not a flat ring. Like, I think if it would have anything, it would be a flat ring, because these particles are all going at different speeds. This would indicate that every single particle is going exactly the same speed, because that's what Kepler's law says. If you're a certain distance from the body that you're orbiting, everything in that distance is going to go that same speed, no matter the mass. So a speck of dust in that orbit will fall to the planet or the body if it slows down. If it speeds up and continues to accelerate, of course, it will leave the orbit and go into outer space. So I think this is completely unrealistic. And over here, when the object supposedly hit the Earth and blew up, notice that we have debris going in every direction there is. The Earth is depicted, and at that time it was, if only cooled with a shell on the outside. So this thing came right into the magma. And a lot of this stuff did not go into the ring. So the question is, did Earth lose a little mass in the process here? Because a lot of this, I think, was just blasted into outer space and never did come back. And it takes a long time for this debris, I mean, probably, I would think, hundreds of millions of years, to form any kind of a flat ring. Now, on these flat rings, you have, the farther you go out in the ring, the slower the particles are going. The closer in on the rings you are, these are like flat rings like on Saturn, the faster you're going. You have to go that speed. And it doesn't matter if you're a speck of dust or a moon. Everything from that distance goes the same speed, and it's all based on the mass of the orbiting object and so on, and speed and velocity of the orbiting body. And then, of course, the last picture is we have this moon here. But this is showing the moon 500 million years later or something. I mean, well, no, about 4 billion years later. Nothing in between. So this is pretty much This is what they've been pushing. I don't believe it really for a minute because uh, there's no ring around the planet now, and how if there was a ring, and the moon had to have formed from this, there would still be debris out there. Because, like I said, everything in that ring is going the same speed. Now, how is it that the moon gathered everything that was over here, even though it was all going the same speed? Kepler's law says that. There's no argument about it. So how could this moon gather anything and form a moon and then have the ring magically disappear? Okay, so this is the, what can I say, mainstream theory. So you can see there's a few holes in that. It just doesn't work. So the mainstream theory states that 4.5 to 4 billion years ago, and at least they got the date right, a storm of asteroids pummeled the Earth, bringing water. In fact, much of the water on Earth is not only older than the Earth is around 1 million years older than even our sun. So it came from a million years away. And look at all the water on Earth. I mean, think of it. That's a lot of water to say just came from outer space. Well, if it just came from outer space, and when these planets were forming, then Mars should have had just as much water too, I would think. And I think it had a lot of water, but it had a problem somehow with the atmosphere, and then it got eventually just blew away. Mercury and Venus, of course, not much chance for water to form there. The conditions just weren't right. Farther on out, we have Uranus and Pluto and Jupiter, Saturn. We don't even know, but it looks like some of the moons way out do have a lot of water. So, it's possible. But how did water get into the dust of the nebula? I don't know. It's just kind of hard to explain. But where else could it come from? So it's kind of like it had to come from somewhere, and that's the only way it could have got here, right? The rest of it was degassed from the interior of the planet. So anyway, that's the theory there, and I think it's probably a pretty good theory. But there's a few things like, why is it so quiet now? And I still don't understand why we don't have rings, and where's all the debris? It's like it's all gone. We have a few asteroids out there, but it's only been 4 billion years. So maybe that's the time that it takes to get rid of all the loose debris around the sun. I don't know. This is a more realistic picture, except for Jupiter sitting there. But this is how the dust would form. Everything goes in the same direction around the sun. We have the comets bringing in water. We have boulders somehow being dragged in towards this planet, or they came from outer space, because they can't just leave their orbit and then just go slamming into a planet, and unless the magnetic pull pulls them in or something. Jupiter, I'm not sure about that. How it's showing it basically with gases and everything already, but we still have the dust here. And like I said, everything closer to the sun is spinning faster. Everything out here is moving much more slowly, and it's all going in the same direction. These boulders aren't just going all over the place. They're going in a straight orbital line around here. And there's no way that this boulder can catch up to this one, as far as I'm concerned, because that means that this one would have to be going faster than that one. Well, if it was going faster than that one, then it would be in an orbit out here. You can't have all different speeds in the same orbit. And so that's something to think about whenever, people are talking about stuff like this, Here's another picture. Not to scale, of course, but it shows all the planets and everything. The comets coming in. We have the asteroid belt here, right after Mars. Seems to fit right in line with a planet. But like I said, all of these asteroids, now the asteroids that are going closer to the planet, depending on how wide this is, are going faster than the asteroids on the outside of the asteroid belt. Okay, so there is probably some inner reaction there. I could see maybe how a planet could form if you get that shape. But why is it still there? Could this, and then they say, oh, and why is it so evenly distributed too? If, let's say this was a planet, and let's say it got hit by something and blew up the planet. It's the same thing that I said before. Everything goes in a 360-degree blow up. You know, a lot of this stuff goes into outer space, never to be seen again. But our mainstream scientists will say, oh, well, there's not enough mass here in the asteroid belt to make a planet. Maybe a small, tiny planetoid. But they seem to, just omit the fact that a lot of this stuff disappeared. This planet was probably, I don't know, somewhere between, it wasn't very small. Or I think the thing would have just been blasted away and you wouldn't even know there was an asteroid belt. So I think it was a pretty good sized planet. And it just got hit by something really big. And the same thing goes out here. I don't know what's going on out here. It's all stuff that's just going very slowly. Maybe it just takes longer to form a planet. I don't know. This is pretty realistic, really. This is what I think it looked like about 4.6 billion years ago. Plates haven't really formed yet. So we don't really have continents. We just have a skin that's drying. And there's no, it's just radiating so much heat that there's no way you're going to form water on that. So I'm trying to present these pictures in order, but like I said, they all interact. Here we're calling a 4.4 billion year old zircon crystal. These are used to just about tell you how old the rock is, because it's only found in 4.4 billion or older rocks. Oldest bit of the Earth's crust is providing new insight into how the early Earth cooled from a ball of magma and formed continents just 160 million years ago after the formation of our solar system. Well, that's a mistake. It's not 160 million years ago. Earth did not form right in the middle of the dinosaurs. It just didn't work. So, it did, 160 million after the formation of the solar system. So it pays to know what you're, to know a little something when you look at this stuff, because a lot of people are so wrong all the time. But that is a zircon crystal. That was I just wanted to show you the crystal, Well, here's the part of Antarctica that's thickest in ice, and this is slightly out of order, but it does show your, down on the very bottom, we have this billion-year-old bedrock. And this billion-year-old rock is actually volcanic. It's sedimentary from the volcanoes and ash and so on, etc. And then below that we would have our, the 4.4 billion years would be down here. This is sediment that was less than a billion years old on top of this, of course. As it was a part of Gondwana and Pangaea. And when it got to the South Pole, Antarctica got to the South Pole about 40 million years ago. It finally settled in. And the ice formed. This took, of course, about 10 or 20 million years for this to form that thick. But this is basically a cross-section of Antarctica. right in the East Antarctica. Okay, I'm gonna stop there and go to some different photos here, and we'll get started on the geologic time scale, which is extremely important because you have to keep referring to this thing constantly. We'll be getting into some real fine detail on Antarctica later, but right now, I guess we'll start about 650 million years ago. That's a little bit it's just before the Cambrian, or when the Cambrian started. There's no life yet, but this is basically what we had. A lot of water. We have ice forming. Now they're indicating that it's a little colder than I think it really was, but they've got indicating ice on the top and the bottom. This is the picture. I don't know if there was ice, and nobody really knows, but it looks good. I guess they maybe want to show the poles. But anyway, this is 650 million years ago in the Cryogenian. Moving up to 356 now, we see we have Antarctica, and it's starting to split up now. Oh, and by the way, I forgot to point something out. Siberia is down here on the lower right. It's going to go up on the top of the globe and come down from the top. Antarctica and Australia are in this area here. You can rotate this thing any way you want. India over here in the middle. You can maybe make that a little bigger. Australia, Antarctica, and India are all one. Down on the bottom we have Amazonia, West Africa, Siberia, even got Alaska there. Okay. So now, 356 million years ago in the Carboniferous, we have the Paleotethys Ocean, Euramerica, and Gondwana. Now we have Antarctica down here. Keep an eye on that. It's still attached to Australia. These rift zones are starting to form. The subduction zones are starting to form all over. This is all still one big attachment. And we have, still a lot of water. The planet is actually pretty warm now, and there's no ice. $255 million. Now this is all coming together up here. This is Gondwana again. We have Australia down here. Antarctica's on the bottom. And this may not necessarily show where the South Pole is exactly. Here are the subduction zones here. So the planet is forming its continental drift now. Everything is taking place. The subduction zones, we have a nice even transition of the planet surface. Now, 94 million years ago, Antarctica and Australia are well on their way. India is on its way up towards China. South America and Africa will split. North America is very interesting. It has a big subduction zone here too. That's why it's such a dangerous place to live on the coast. We have these mountains. Well, those are all volcanic mountains formed with the subduction plate here. And also land is accreted as this part up here on the left slides to where the arrow is going. Some of that stuff is scraped off, and it will actually form like coastal ranges. And you'll find in coastal ranges that the sediments will be from the ocean bottom. Well, that's how they got there. I can't think of anything else interesting to say here. India actually does kind of come over this way a little bit before it takes off. But here we are at 50 million, and Antarctica has pretty much reached the South Pole. Everything is starting to take shape. The inland sea is going away here, but the subduction is still going on, and California is forming. We have quite a separation here. Now only 21,000 years in the Quaternary, which is in the Holocene. Everything's pretty much in place. Okay, we've got ice top and bottom, and we're still showing the nice subduction zones here, which, by the way, is the ring of fire now. Because these plates, here's what's the deal. These plates, where you see the orange, there's a subduction zone there, and you'll see this later on. The reason you don't have the ring of fire out here in the middle of the Pacific where this rift is because that's a spreading zone. This is all it's doing is the magma's coming up here and it's spreading. It piles up here and it pushes this way and it pushes this way. And that's a subduction zone, so it's been pushed out right away under that. Anyway, yeah, it's pretty interesting there. Here's probably an out of place picture, so I'll put it on hold for a second. Well, actually, we don't have to put it on hold. You know, this is the wind map, and it's different at different elevations, but Antarctica seems to have its own little system here, just like it does in the North Pole. And believe it or not, I don't even know if it rains at all in Antarctica, but I do know that it snows very little. You would think it'd be snowing like crazy there all the time, but really, it's dry, and it doesn't really snow that much. I was surprised to learn that. Just a shot of Deception Island. Now, this is one of those volcanoes that forms right off the coast from the subduction plate. Where the magma comes up, and this is actually a ring. That's a ring that goes all the way around, and there's an opening you'll see on the left there to the ocean. And I think there's even a small, there's a couple outposts there too. Going back a bit, we have Pangaea, just showing that, you know, the mass and name, Tethys C, Pangaea. Then later, when it splits, see, then you have Laurasia and Gondwana. They're claiming this is 160 million years ago, but I don't know. The main thing I want to show is Laurasia and Gondwana. I know those are hard to remember because you get them confused with Gondwana land and so on. Just a quick shot. These guys are all together here. Antarctica, India, Australia. And what happens is there's actually these are plates. These are separate plates, but they're pushed together. There's not really subduction zones right around here that would make them split apart or anything. Or spreading centers, I mean. Another view. Not much to see there. I think they're showing Antarctica pretty much at the South Pole there. Cross sections are the main geological tool. This is, of course, as labeled, the Antarctic horst. And you can see that most of Antarctica here really is just volcanic. Coal seams, okay. But we have volcanic, these are dolerite sills, which is carbonate. We have Cambrian, granite down here, and so on. You can kind of read the picture here. But there's two different interpretations of the same place. So, done at different times. In the background, we have folded sedimentary rocks of Precambrian. That's as old as it gets. Age in isolated mountain range about 500 miles from the South Pole. But we see that we have this as sedimentary rock. So that the only way that sedimentary rock can come is from when Antarctica was attached over with Australia, India, Gondwana. Glaciers, which is the main dynamic moving force of Antarctica rock. Yes, there are plenty of fossils. These would be in the peninsula up towards Argentina. It's mostly where the fossils are found because the land hasn't been ground off by glaciers. This is a high mountain, but it's not as high as Mount Vinson, which is the highest mountain at 4,800 meters. This is actually on an island, and it's an active volcano. Oops. This is Greenland, but the idea here is to show the glaciers. We have all of these valleys. The glaciers are just pouring down these valleys, just grinding them down. I thought that was kind of unique, but you don't see this kind of a pattern that much, where they're just straight lines. Then we have, this is a glacier over here. It's all emptying into the sea. Back here is very interesting because we have the glacier sliding from the right to the left on the mountain between those mountains, but we have glaciers joining from the top, but then it's flowing down towards the bottom of the picture at the same time. Same process in Greenland that's going on in Antarctica. Whoops. Well, now here's a good picture. I like this one because it really does show what's going on with the ice. When Antarctica first arrived at the South Pole, it didn't really have much ice on it. Hardly at all. It was starting to get cool, but the planet was pretty warm. So you didn't really have that much ice. The numbers indicate here that it was basically there for about 3 or 4 million years before ice even started to form. So you can see that it's not even covered with ice. This is saying here 34.9 to 33.6. Well, there's apparently in just a million years or so, all of this ice formed. So apparently the cold age started then, because Antarctica arrived at the South Pole it was 40 million is when it was almost stopped. It got there, it took 10 million years for it to get, all the way across the Arctic Circle here, which goes around it. So before we actually get into Antarctica in fine detail, let's get back to this, because you really need to see this in a perspective. And the best way to see that is on a geologic time scale. And this, I think, is such a great one. And they've got this divided up to these columns here on the left are in the Phanerozoic. And then we have Phanerozoic and Precambrian on this far right one. And it basically starts off like in million-year increments. And we have the Phanerozoic with the Proterozoic, and so on. Everything has a name here. All these times. So if you're in a certain rock, you know where you are too. But the formation here, they're pretty much have it down at about 4,600 million years ago. Over here on the right, you might as well see this. This is the polarity map for the polarities that you see in black and white there. Those are all polarity changes of Earth. Okay, right there. So it's flipped a lot of times. This has happened so many thousands of times. We have normal as black, reversed as white, uncertain. These are subduction zones. You'll know all about that. These are spreading centers. Now, if we look at this one, here we are at 650 million years ago. Well, at 650 million years ago, it wasn't as all serene as it looks here on the right. This is volcanic. There's a lot of volcanic. There's all volcanoes. All of this is volcanic rock here. And then we have the volcanic rock sediments and ash and so on starting to form. And underneath all of this is this old bedrock. And I'm saying that there's volcanic activity on top of the 4.5 billion-year-old rock that was the first to form. So if we move over to here, and now we're up to the 514 million year Cambrian mark. We have Gondwana. I can't even see it. Okay, 425 million. 356. We've seen these already, I think. 255. And we can see how it just kind of went together. Now, over here on the far left scale, it's like a zoom in on about 5 million years, I think, here. Yeah, 5 million years. Now, the record only goes back 5 million years, but on this band right here is the temperature of the planet. And it was, warm 5 million years back. They're considering it to be pretty warm. So you can imagine how warm it was back then. And as we go up, it's getting cooler. Cooler and cooler and cooler. But notice that the lines, long before, mankind came along, humans, notice and this is 500,000 years ago. And notice the extreme fluctuations between cold, hot. So these are ice ages. When it gets up here, those are ice ages. They never had an ice age back here, it looks like. But then the record doesn't go back far enough. It doesn't go back 38 million years, and we know there was ice forming, so the planet did cool 38 million years ago. Started to cool, actually. It probably brought it to this point down here at the bottom. Okay, so over to here. We're going to start back to 540. I just want to cover the charts here so we can see what's going on here overall. You don't have to really remember all these names, but here's the ocean sea level on the right here. This is what this one is, sea level through the ages. So they've got it at 540 million years ago. The sea level being very shallow. So we must have been continuously bombarded with more comets, because the water level seems to be going up, and I'm not sure if that's because more land is forming and so it's just taking up more space, or is the sea level really rising? Anyway, that's the record of the sea level, and up at the top we have it in meters, down to 100 meters there, 200 meters plus over here. Right now we're at 0. So that's where they have the scale set, is right now it's at 0 over here at million age 0 in the Pleistocene here, Quaternary. It's right at the 0 mark. So the trend looks like it's going down. But if the ice is melting and it's getting warmer, this should fluctuate, and yes, it could go up, but how high is it going to go? I think the maximum it can go, if you look at the record here, is about 200 meters. So it could be that the sea level could still go up 200 meters. That's a lot. So if we were just using the time scale alone here, we could say, well, if all the ice melted, then the sea level would go up 650 feet. But I don't know about that, because when the level goes up, the ocean spreads out too. It's got more room to spread out. So I don't know if it really goes up that much if it's spreading out. So you have to consider that too. The actual level that the ocean is going to go up, if you don't include the spreading out anywhere, where it takes over land, would be 650 feet. But if you subtract out that, I mean, it would go up 650 feet if it didn't spread out. Once it's all spread out, then we're talking more like 400 feet. So we have the polarity. Let's start back at, well, they even have it over here. They do. 540 million years ago, we have polarity. They're not sure. Can't blame them for that. Looks like it was reversed a lot. You know, I mean, the magnetic field situation here is very chaotic. They don't know, so it was probably reversed. Or it means they just don't have samples. And it's the same thing over here. We had a long period of, over here, 125 million to 80 million years. Well, it's about 40 million years. It was nice and north. But then look at all the flips. Boom, 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 boom. It's like, you know, every million years or so, and then all of a sudden, nothing. And then more and more reversals and just flipping like crazy. But notice the last part here. We've got a solid block there. And when we come over here, we see that the polarity has not flipped for, let's see, 5, 6, well, 700 something. Oh, I guess 0.78 million years. So that's quite a stretch. But if you look at the rest of this, I mean, doesn't it seem inevitable that it's going to flip? But that's only, what, 700,000 years. We saw over here it had held for millions of years. And down here it held for, well, 500,000. I don't know. I don't know about that one part. You know, that one part right here almost looks out of place. That it was, they're calling it normal for, 40 million years with a couple of tiny reversals in there. So anyway, there's the polarity chart. So if everybody's worried about the polarity changing, yeah, it could happen any day. And does this show any correlation between polarity changes and sea level rise? Well, if we look at the lines, I mean, this is so bumpy anyway, but it looks like it's pretty rough here, and this was pretty steady, so it doesn't look like anything's really related there. We do have the planet is on a cooling trend, but here's what's confusing. It's cooling, but it's such a jagged line, I mean, this is 25,000 year, it's just a small piece of this. So who knows where this is going to go? Maybe it's just going to keep on going. So anyway, this can be had online as a wall poster. It's pretty cool. Not sure about how accurate, but I think it is pretty accurate. To tell you the truth, I like to use this other one. But if you just need to remember, the names of everything, this is probably the best, easiest one to have. Just have it like a pocket version of it, and then you can just refer to it. It's not overly complicated. It doesn't have all kinds of charts. So here's one showing the history of the Earth. Starting at 4.6 billion, Earth and Mars form, and other planets. 4.5, proposed new start date for life on Earth, and they mean the simplest, most primitive one-celled creatures. Now we've seen what it looks like at 4.6. It just forms 4.5. That's like what? It's 4.5 billion. So they're giving it 100 million years for life to start. Well, that means then there had to be water. It's not going to start if there's no water. 4.2 billion oldest fossils showing life thriving away. It's still pretty primitive life, though. 420 million. Plants begin to colonize land, probably because there's an atmosphere now. The UV light is being blocked. Plants can grow now. Animals can come out. They came out later, 350 million years ago. We have 230 million. We have first dinosaurs and mammals. So anyway, that's kind of interesting. And it shows the ice ages here too. We have ice ages. So, I don't know. I don't think this is all that accurate. Life and oxygen, this is sort of important. I don't know about the dates, but the point is that cyanobacteria were known to be carrying out photosynthesis 3.5 billion years ago. So it's a long time. So we have carbon dioxide plus water plus sunlight equals organic compounds plus oxygen. And you can read this whole thing here. So oxygen is growing. The more plants you get, the more the oxygen forms. This is really, you kind of need this, these fossil charts, because you can use the fossils to date the rocks. And the fossil record is incredibly well done. They've been doing this for 200 years. So we've got just about any fossil you can find, unless you find something new, you can tell where you are. So if you're finding these little one-celled certain creatures, then you know you're 540 million years at least. So down here is when things formed, more like stromatolites in water. But you have to have the water. So that means that the water was formed already. And of course they're showing it formed already at 4,500. But I don't know. That's pretty fast for the water to form, and this planet's still not being bombarded constantly. Cambrian, that's about where back on the other maps showing Gondwana and so on, this shows that by the time it gets up to, 65 million years, and Antarctica is on its way. It was started to break up, remember, back in this area here. So Antarctica and Australia were covered with animals. Another interesting chart. Core formation, moon formation, and they're showing the impact. I don't think they really know that. Zircon up there at the top. Late bombardment. And I don't know why they're showing the Earth blue, like it had water already, and then it gets hit and the moon forms. Something wrong with that picture. But we have the Costa Nice down at the bottom. That's well, it's probably in Australia too, but it is in Antarctica exposed. What else is there here? Not much. There's a trilobite. Those are actually pretty recent. I mean, if you consider that millions of years. This is a nice one too. It looks funny, but everything's there. Cambrian. Before the Cambrian, there was life, but it was just so primitive, and it just went on primitive like that for a billion years, a couple billion years. Primitive life for billions of years before finally things start to, form. But all these fossils can be used to date any of these rocks. You find this weird creature here, well, you know you're in the Miocene. 2.3 million years ago. Or is that no, it's 23 million years, sorry. Another map showing the directions that these guys are going down here. All of the yellow: Antarctica, Australia, India. They pretty much broke off from West Gondwana and just went their own ways. India, 120 to 20 million years it took to get there. They've got dates here. 45 million years it took Australia to get to its spot. So about 200 million years ago, this is what Antarctica looked like, and Australia and India. And as it broke away from Gondwana, it was covered with dinosaurs, plants, everything. So it broke away. It was independent of the main continent there, and it had dinosaurs on it. This was as it was moving towards the South Pole. Unfortunately, 65 million years ago, before Antarctica arrived at the South Pole, there was a mass extinction. Probably a major asteroid impact. These creatures were pretty, some of them pretty strange. These are the Grand Tetons, but they were formed by glaciers. Same when the North American continent was covered with ice, glaciers. And basically here's the glacier action. This is what happens in Antarctica and everywhere. Here's a few of the names of the different features. This is the main glacier. These feed off into here. From here they form in these little, they're called cirques. The arete, of course, is the ridge along the top. The one that I showed you of Greenland, the tops of those mountain ridges you saw were the aretes. Very sharp, U-shaped valleys. One thing they don't show here is that these are actually hanging valleys, because this has been sheared off down here, and the glacier actually pours off the edge. When all this ice melts, you'll see these hanging valleys. It'll just be a cliff wall all along here, and then you usually get like a waterfall pouring down. Here's the transatlantic mountains, or I mean the trans-Antarctic mountains. They have, this is the ocean to the right, and glaciers are actually passing through these mountains farther down here. Here's a map giving you the idea of how high Antarctica is. Mount Vinson is 4892 meters, which is about 15,000 feet. Australia doesn't really have much here. It's 2,200 meters. Antarctica, early on, This looks like it might even be before the dinosaurs got there, or just about when they got there. It's about 200 million. Well, it's about 250 million years here. Again, a cirque, the arete. Almost every mountain in Antarctica, it looks like this. An old picture showing a big, huge glacier coming here, and then this one is supposed to be feeding into this, but it looks like it might have melted back a little. And also this line here is kind of telling. Also, we have the hanging, a little bit of a hanging valley there. Looks like this ice has melted a little. Same thing. This was done by glaciers. The political map showing that everybody has a hunk of Antarctica. And of course, the United States not only has bases all around the edge, but they have one in the middle, right at the South Pole. Yes, Amundsen Scott. He was an explorer. Well, they both were. And who knows what's going on there, because we're not allowed to see within this 80th, what is it, parallel? 80th. In Google Earth, it's completely blurred out. You can look at maps all day, all over the place. Nothing will show anything in here. Transantarctic mountains are also blurred out all along there. Even though the base is at the South Pole, they still have access, seemingly unfettered access, to this mountain range through here. I personally think that because since everything is being hidden, we can't see anything. Google Earth will show us nothing. Other maps will show us nothing. There's got to be something big, secret going down there. I think it's much, much bigger than what we're told. They probably have quite an underground situation going on there. It depends on where it is. You can't really build an underground base in ice that's constantly moving, but they can burrow down through it to the ground, and they also have access, like I say, to these mountains. They can build as big a bases as they want. They can bring that big tunnel machine up there, drop one off down there, which they probably have already. They probably have tunnels all over the place. I don't know that for sure though, but I would imagine so. Why is it so shrouded in secrecy? You know, they don't hide things that they don't have to keep secret. Well, or should I say, they hide things they have to keep secret. So therefore, there is something secret. If you're looking for fossils, Dinosaur Cove's the place to go. And keeping in mind, this was attached to Antarctica at one time. We're talking 100 million years ago. It's not even in the Antarctic Circle yet. And that's where a lot of fossils are found, in Dinosaur Cove, and also the rock is the same too. So it's kind of obvious that was attached. Here's some fossils. Looks like ammonites. Ammonites now reside in Chile at the museum. More of them. The rocks that we're focusing on come from the end of the age of dinosaurs. See, so you can use these to date the rock, and look, 67 to 71 million years. This is where they find the fossils. This is what the seafloor looked like back hundreds of millions of years ago. All of this stuff is used to date rock. All of these fossils you see, these aren't fossils, but they will be. Everything in here can be used too. Here we go. This is probably the Permian. More dinosaurs. trilobites. What was it, 600,000 years ago? And there's all kinds of different trilobites. You can use those to date the rocks too. 280 million year old fossil tree stump. That's what that is. And we know that Antarctica was part of Gondwana back in 280 million years. Plants grew on what today is the iciest continent from 400 million years to 14 million years ago. So after the ice formed 38 million years ago, plants were still growing. The forests were still there, but everything was slowly dying off. There's the moon. We don't know how it formed. There's Earth today with its atmosphere and its haze. I'm sure it didn't look like that 100 million years ago. Fossil tree stump. Here it is in the ground. Notice the sandy sedimentary rock around it. Another view of the tree stump, and notice the shape of the bark. Really ridgy. I don't know why that's there. Doesn't hurt to go over it again though. So 356 million, so that's almost 400 million. It's still attached. And the dinosaurs came what? Oh gosh, I think it was 250 million. Here's a map showing the likely impact of a comet which probably broke up before it hit the atmosphere. And since the Earth was rotating, it did a nice little spread pattern across the planet here. This rose the sea level up, I think, probably about 400 feet. But then with the spread out, it was a little less. It's actually gone down 200 feet since. So the most important thing about geology is the rocks. Now, here is how you would test the rocks to see if they're carbonates or not. And there's a whole bunch of different rocks that are carbonates. And like, for instance, the limestone blocks that they use on the Giza Plateau and all the pyramids. Not all of them had limestone, but limestone it dissolves in acid. And I always thought that was a poor stone to use, because if you look at the way the limestone weathers, it looks like somebody poured acid all over it. So why would you want to build something that's going to last forever out of limestone? So that was a bad choice. There are some other better choices. But this is basically it. You know, this is a piece of magnesite up here, just magnesium carbonate. Iron carbonate would be siderite. And here are the formulas down here if you want to look at that. But the precipitate is carbon dioxide, water, magnesium, and chlorine. Here's the chart. What you would do is you would carry your little bottle of hydrochloric acid, and if you warm the acid, you can see what the reactions are. So we have, dolomite. Supposedly they used a lot of dolomite in Egypt. Warm acid, yes, weak. Looks like magnesite would have been a very good choice because it's very weak. Down here, siderite, weak. Down here, witherite. But limestone, I don't know. I think that's calcium carbonate, which is like aragonite. Strong. Worst possible choice. Now these are minerals. This is peridotite, igneous rock. So when it cooled, these minerals formed. In fact, rocks are minerals. It's just a combination of minerals and elements. And elements, some of the elements are minerals too. That would be gold, silver, copper, sulfur. Here's how the minerals form. Basically, just a kind of a easy diagram here. These are xenoliths, and in there you'll find the diamonds, other gems and stuff. And this is basically, they call this a pipe, and it's an old volcano where it uh, died out, and the magma was in there, cooled just at the right temperature, had the right amount of minerals in it, and you get diamonds. This is the, oh, and it's called Mar, this part here. Peridotite. Specimen shown is about 2 inches 5 centimeters. These are gems the way they're found in the ground. These are minerals. Oh, and this goes on about how the red and blue spinel was confused with ruby and sapphires for 1,000 years. Spinel. So here's tuff. You're going to see a lot of this. Basically, it's this volcanic ash. When you have a big blast from a volcanic or whatever, you have that tuff, or the ash flows down the side of the mountains where it's half flames. This is the kind of stuff that buried Pompeii, and it's called tuff. Very easy to recognize. The softer part is just ash. And depend on how old it is, how hard it's going to be. But you see this everywhere. Everywhere there's a volcano, you're going to find tuff somewhere near it. Hornblende. Well, here's the read-up for that. Here's the formula. And when you take that mineralogy class, you have to memorize every single formula, and it was the hardest class I ever took in my life. I learned a lot, but you know, I had trouble memorizing all of these formulas, and because there were so many. Double chain, inosilicates. Everybody knows what this is. Biotite hornblende granite. That means that these black things are high biotite and hornblende. This, well, you can hardly see this. Anyway, it's biotite, granite. There's all kinds of different kinds of granite. It only depends on what kind of minerals are in there. Rose granite, all kinds of different granites. There's another popular rock. This is an igneous rock, but extrusive, which means that it is not in the ground anymore. It came out. Hornblende sometimes crystallizes below in the magma before eruption that can produce large phenocrysts of hornblende in a fine-grained rock. Sodalite, another mineral, rock forming, used as a gemstone. Sodalite occurs in igneous rocks. So if you're looking for sodalite, you need to look in the igneous rocks. Crystal sodium-rich magmas. Sodalite granite. Now that's pretty granite. I'd like to see a pyramid made from that. Olivine gemstones, another mineral. These obviously, I don't know if they formed like that. This has been a nice, something nice to build a temple out of. Olivine and palisite. Here's a subduction zone drawing. You can see that we have volcanic activity forming these mountains here. And this is actually, you could even say this was California. They've got the coast ranges right here. This is like the west coast of the United States. Here's that big subduction zone that you saw on the maps. You can get volcanoes out here. Depends on how thin this is. This is the spreading zone out in the middle of the Pacific. Notice it shifts. It's constantly broken up. These mountains here, mostly, well, in California, granite. And a lot of this that you see here, this is volcanic, but it also, this gets scraped off and deposited up here. And in fact, all the coast ranges are seabed sediment. Antarctica again, showing your subduction zones. Another strange map. I haven't figured this one out. Why it says Gondwana over there, I don't know. Another shot of the Trans-Antarctic Mountains. And we have that same subduction zone right here. The mountains, volcanic, Mount Rock, all through here, all around out here. In fact, everywhere you see a star. So here are the Trans-Antarctic Mountains here, real simple drawing here. This is why we see volcanoes and islands off the coast of West Antarctic. This is the East Antarctic lithosphere. So you can see it's almost, we're talking about two different, and this is East Antarctica, right here where the water is. Another view of that. This one shows important glaciers, Trans-Antarctica Mountains, Ross Ice Shelf, glaciers coming down through here, and the glaciers are actually pouring through these mountains. Right here, everywhere you see these glaciers, Shackleton Glacier, those are actually pouring from the high ground. This ground over here, by the way, is really high, and the mountains are high. They look high because this is really low down here, but on this side the mountains don't look so high, but the glaciers just literally pour out between the peaks, just grinding them down still. They're still forming, but they're also being ground down. Plate map of the world now. All these are the plates. All that you saw formed billions of years ago formed into plates. And these all are sitting on top of the magma. Even this is a plate. It's a spreading zone, but it's still a plate nevertheless. Here we go with the subduction zone. Goes down. This is moving, but it's going down. Magma comes up, forms land here, coast ranges. This is how land is formed. Another nice drawing showing everything you need to know, really. Continental, this is how the mountains are forming over here. We have spreading zones. Volcanoes here, there's like a hot spot. These plates will move over a thin spot in this lithosphere here, and you get like the Hawaiian Islands. It's a perfect example of this right here, called island arcs. In fact, Yellowstone is over a thin spot too, and the crust is actually moving over that Yellowstone area. So they keep saying it's going to blow, but I think when it blows, it's not going to blow in the old crater, because the old crater will be over new lithosphere by then, and what we'll have is it's going to blow somewhere next to the Yellowstone, which will make it just as disastrous as it ever was. Another map. Kind of hold it there and look at it if you want, but I'll just move on here. Spreading zones. And I think after you look at all these maps, you can see this is how continents are built. right here. Dry valleys. You can read up here, but it says basically that it is just so cold and so dry that the snow just won't stay. It just literally evaporates. Now, it looks to me like this used to be a glacier valley by the shapes of the mountains here, but with all this talus, it looks like it's been a couple million years since we've seen a glacier here. Here we have two completely different types of rock. I mean, that could be magnesite or something. It could be a carbonate, who knows? This definitely looks like some kind of sedimentary rock over here. It could be igneous without actually looking at it. I don't know. Now these are ice flows. Now these are the ones that come out into the ocean, and these things break off. They can only extend out so much before the weight of the ice just, they just break off. That's perfectly normal. So just because you see a crack going across one of these doesn't mean anything. It just means the ice is so heavy it's just broken off. Doesn't mean it's the end of the world. And by that I mean, here we go. This is the ice shelf. Here's the sea level. They break off. They float out. We have icebergs. Ocean water down here. Warm water always grinding at the bottom down here, wearing this down. But the ice is flowing, so is it wearing it faster than it's flowing? We have also down here, where this is scraping on the bottom down here, grounding line. It's melting here. So it's not just melting up here, it's melting, all this is melting. And this could be melting, that shelf could be way out here, and this could be melted all the way back to here, and you wouldn't see it from the surface. And a glacier trying to get into the dry valley. It's just too dry. There's just no humidity whatsoever. It doesn't rain in Antarctica. Another interesting rock formation there. This is what's there now. There's plenty of life in the ocean. There's a seal. There he is again. This is all underwater ice. So it's a whole new world there. Okay, recent life. That's growing there right now. You can tell by the man. A million years from now, these will be fossils. Oh, wait a minute. I might have something important to say here. Look like sponges. Quite evolved. They're invertebrates, but the larvae have spinal cords. So I wonder how long those have been there. So there is life, and it's under the ice. So here's the famed Lake Vostok. And the Russians are over here drilling a big hole. It goes down 2 miles. And this is basically what they've come up with here, that there's this huge, biggest underground lake in the whole world. And then the water is melting because of the earth here. And so it's melted away underneath the ice and it's flowing out this way. 90% of the world's fresh water is in Antarctica. We're going to be in trouble if Antarctica ever melts. Here's what this guy used to look like, probably a million years ago. Antarctica again. The huge glacier here, this whole valley here, just pouring out, just scrubbing and grinding, grinding, grinding. Nice shot of a dry valley here. Now I want to explain something. This valley is a U-shaped valley. And notice the shape of this valley. This glacier, probably millions of years ago, was way over here. This whole place was covered. This is glacial moraine. There was glaciers coming down here, through here. You see the cirques. You see the arites. This is glaciated, all of it. But it's a dry valley now, so the climate has changed. Oh, here's another one of those ridiculous pictures. Oh, there's no way all this heat would be out here like this. This is kind of like, it does show the rings sort of right. And then just for general knowledge, stars, little chart. Now, if it's a mineral, these are the 5 criteria. Naturally occurring, inorganic, solid, can't be water, definite chemical composition, and a specific atomic arrangement. That would be the mineralogy. Few more examples of how lush it used to be. This is a map showing the actual bedrock that's above water. I mean above the sea level right now, even if it's covered with ice. Another map showing Antarctica bedrock. Everything in blue is below sea level. And you can see where the highest mountains are over here, over here. Everything in orange or red is the mountains. These are all covered up. You can just barely see the tops of these mountains. So they're saying that the universe formed 15 billion years ago. Galaxies formed from stars, dust, and gas. Earth formed 4.6 billion years ago. It's kind of funny to think that the universe is only 15 billion years, and before, like 5 billion years ago, there simply was no Earth. This is real. This is not just stained rock. This is the color of the rock. It's full of copper. I wouldn't be surprised if, I don't know what that would be. I couldn't really find out what type of rock that actually was. But this is not something that you would find anywhere else but Antarctica. Another shot showing early formation. I would guess this would be, we have a moon out there. So this is probably between 4 and 5 billion. Probably closer to 4, maybe 3.5 or 3 billion, because we've got an atmosphere here. Now, here are the fossils that they've moved this back to 4.5 billion years that these formed. These are stromatolites. On the left here would be the fossil. Photosynthetic prokaryotes found in dome-shaped rocks called stromatolites. So somehow they used the minerals and formed these strange looking rocks. Here, now they're saying it's only 4.1 to 4.2 billion years old, which is probably more accurate. I can't see it going back more than that because it was just too hot. And life originated in the oceans, of course, between 3.4 and 3.9 billion years. Probably because the atmosphere was still forming. There was really not that much air. Here we have some of the rocks that you'll find in Antarctica. This is felsic garnet with biotite, quartz, and magnetite schist. A lot of minerals in there. pretty much been over that. Oh, now here we have, this is what a glacier will do to solid granite. Now if you go up to Lake Tahoe or anywhere near Lake Tahoe in the mountains where the glaciers were, you can find a lot of glacier polished granite. And it'll be a lot smoother than this, like up over here. And it would just be still shiny. After thousands of years, still shiny. And the glacier to come rolling over this thing here. This is probably a ancient granite batholith in the Sierras. Okay. Now here's the official story here. As it cooled, it was cool enough for water vapor to condense and fall as rain. And then we start getting water. About 245 million years ago, about when the dinosaurs became amphibians, were coming out of the ocean, and dinosaurs were starting to grow. We have one ocean formed called Panthalassa. Now that's what the whole Earth was, just an ocean with this big hunk of land in the middle. Atlantic and India formed first, about 180 million years ago. Now they're saying that the plates, by the way, are moving about 10 centimeters a year. So you can figure, well, in 10 million years, how far is your continent going to go? Sedimentary rock. This is Jurassic. And these are volcanic sills and this is sedimentary, but it's probably volcanic ash, or it's incredibly small flows. But then we had some really big ones here. Strange thing, and you look how thick this one is. That's one flow, one volcanic flow. And of course the Jurassic, is 200 million years ago. So that's when we had Antarctica breaking away from Gondwana. And there was a lot of volcanism at that time. A lot. Here's some more of the more beautiful rock you'll find down there. It's K. feldspar pegmatite. And this is from the Larsman Hills. Imagine a temple made out of that. K. feldspar quartz gneiss. Looks a lot like granite. This was from around a place called Mawans Station. Larsman Hills again. K. feldspar pegmatite. Another stunningly beautiful rock. I mean, if you were to grind this off and make it flat, it's just really pretty. Major events. Here we have some of those prokaryotes, known also as stromatolites, 3.5 billion years ago. Myelinite from Mawson's Station. Another beautiful temple building rock. Just quick facts about this. We're about 25,000 light years from the center of the galaxy. And here we have the prediction for how long we're going to last. Another 1 billion years, all oceans and rivers will have completely disappeared. And it'll be 160 degrees Fahrenheit. And that's not that far from now on the scale here, but of course we got billions of years. So it'll be inhabitable for another 500 million years if we protect it. But if we don't, well, I don't think that's going to have anything to do with it. As far as the sun's concerned. Now they have this second and third atmosphere. The first atmosphere was no atmosphere. The second atmosphere, or the first one had no oxygen or anything. The second atmosphere, they're calling it at 4 to 3.8 billion years ago, composed similar to gases released from volcanoes, water vapor, nitrogen, no oxygen though. So we didn't have plants or animals yet. Large concentration of gases in the atmosphere, 100 times that of today's, and it says the greenhouse effect keeps the Earth from freezing. Now the third atmosphere is the one we have now. It's mostly nitrogen up here, 78% nitrogen. We've got 20% oxygen, and the rest is all the rest of this stuff. They're telling us that 400 million years ago, this is what we had. Which makes sense, because that's when the animals and the plants proliferated. You need oxygen, period. Here we have some pale blue, greasy, rulated blue quartz. Antarctica rock. Here we are back at Pangaea. Never hurts to glance back at these anyway. Pangaea, 225 million years ago. Don't hear that word Pangaea because they have these divided up here in the Gondwana and Eurasia, America, Eurasia, and so on. We've been there, seen that. Another map showing important places. This is the ice flow map. Here's the only map you'll ever see that shows the actual shape of the continent right here. Now, I can use this to explain a few things too. Now, notice that we have the Transantarctic mountain range right here. Okay. The South Pole is right here. And this is West Antarctica, all through here. This is all volcanism down through here. And that subduction zone I showed you was right through here. So this part here is going up and slamming up against these mountains. This is all magma that's come up from the subduction zone and creating volcanoes. And there's volcanoes all over the place. And in fact, Antarctica is covered with volcanoes, but they go way, way back. I'm not saying they're active now. But they're just ancient dead volcanoes. A lot of over here, they just sort of pop up all over the place, but mostly through here, like right here. The Hudson Mountains, there on the left, right there in the middle now. That's the Hudson Mountain Range. You see this little trough here. There's giant glaciers coming through empty there. All of this, all these smaller glaciers come in, they empty into these channels, and they just empty out into the ocean here. All of this comes out here. We got glaciers coming from up here, down through here, all over here, and they all empty out into here. All of these, everything you see is being ground right now, ground down by glaciers. Been ground down by glaciers for millions of years. So, if you had any kind of a base or anything, you can't really have it in a glacier. And all of this ice is moving, and I'll show you in a second. It is. Furthermore, any megalithic structures that even if they were built here, like a pyramid or something, it would be gone. It would be just ground down and gone by now. Because remember, Antarctica showed up here 38 million years ago. Pretty much made its home right here. 38 million years ago. 35 million years ago, it started to be covered with ice and glaciers. No one's going to build a city in that kind of a situation where you have ice and glaciers and everything. Now, they might have bases or tunnels into the mountains, but you need to know where the mountains are. So you know there's not going to be anything over here or over here. This is all volcanism here. Not a real good place to, put your underground bases or anything. But over here at the South Pole, you've got access to this mountain range here. That's a pretty sizable piece of land right there. And there also seems like there's a big depression here, but the ice is incredibly thick over here. 2 miles thick back here. And these mountains just barely stick out. Because normally what you see is this. This whole area that you see up here, I don't know if you can see this. I'm not sure if I have my green thing on. This is all high ground up here. It's all high. That's why this looks so tall. But behind it, it only drops down a little bit, and there's channels that the glaciers are pouring out through here onto this ice shelf, which grows and grows and grows. But it keeps breaking off. And all around the edge here, you see these little ice shelves. The Hudson Range over here doesn't really show the mountains sticking out, but these are volcanoes. There's a couple over here, all around. So, going back here, all of the ice from this area coming out here. This is all going out there. And let me show you the ice map. Now here's the ice map. The green lines are is the ice flowing. This is the pattern. You can see what I just explained about the ice flowing out between these tall mountains here off of the high ground. This is the highest of the high ground right through here. All the ice is melting, grinding, grinding, grinding. And all of this is being worn away. All of this ice here empties out into this bay. All of this ice here pours out here. And they actually have an animated version of this too. All of this ice, you can see how it's just constantly forming and just runs off. So there really not very many choices. You wouldn't want to build anything in here where these green lines are because it's flowing too much. Even that Russian supply base that up there that's on the Strava map and so on, that runway is on a glacier or moving ice. So you're not going to build underground tunnels and everything in a moving glacier, okay? So when somebody says, well, they got a big underground base right over here, you look at that and you go, well, yeah, that's a glacier. I doubt it. Here's another flow map, same exact thing, only the lines are different color, a little bigger. All of these little spaces between the peaks. The glaciers are pouring out. This is the Ross Ice Shelf here. This is basically just a satellite view of Antarctica. And if we zoom in, this is probably the best map you'll ever see of anything going on in the circle of silence. South Pole is right here, so the American base is somewhere in there, but they have access to these mountains all around. Just another land map. More map. Now this is more or less the thickness of the ice, I think. Just really super thick over here. This is the thickest place. I guess that is the thickest ice in Antarctica. Right there where that blue spot is. Another satellite image. It's that same picture, only it's got labels on it now. It shows you everything is Ross Sea, Ross Ice Shelf, IS, Ice Shelf, Rhone, Ice Shelf, uh, Filchner ice shelf. Research stations. So they're all over the place. It's not like nobody's down there. Here, this is a map showing how the ocean floor looks around it. It's kind of cool. You can see the spreading zone coming through here. The spreading. This is going that way. It's fractured pretty badly. There's, well, that's New Zealand over there. Australia's right up here, but we see this other big spreading zone right here. And these things are all in between these continents. Now these are the actual, this is like an ice velocity map. And over here on the left up here we have meters per year. Okay, 3592 is the most. The blue, of course, is the slower moving. So up here we have slow or not even existing, any ice that's really moving. This ice is really going fast. This is the ice shelf. This is over water, but it's extending out 3,600 meters per year. That's how far that thing grows. So naturally, it's going to be breaking off. All of this ice flow in here, really going fast through here. Notice how fast it goes through here. This is 3,000 meters a year. So this, they're just, you know, literally pouring ice. And all the while, it's grinding this continent down. It just keeps grinding it. And sooner or later, in more millions of years, there might not even be any mountains, or there'll just be mountain peaks sticking up, and that's it. We have lots of subglacial lakes. Here's Lake Vostok, and in fact that's where I think the thickest part of the ice is at too. And we have more ice velocity here. They're showing 3916. That's almost 4,000 meters a year. And these are the plates or lithospheres. This is a very nice map that shows the ages of the lithosphere. Oceanic lithosphere, that is. Now these are like the ocean, the plates. Now the red is brand new material, and it piles up here, and then it pushes out this way, and then in both directions. So that's why it's pushing this way, it's pushing that way, because it's building up. But then we have the same thing going on over here too. So this is pushing this way. And the red is, well, you can see the color code down here on the bottom. So the farther away you get from the spreading zones, the older the material is in millions of years. So you can see, let's see, it takes 120 million years for this material to get from here to there. 140 maybe. So where are we over here? Over here. This material, actually, well, this is a subduction zone, but it'll take 140 million years for this much displacement to happen there, whereas over here it's a smaller distance. Another ice map, blue color around 50% transparent with a grayscale. Solid light blue areas are ice shelf. That would be down here and over there. And we have the rock outcroppings here. That would be the yellow spots. So you can see the mountains only pop up a little bit up there at the north, over here on the east, and down west. Now, so this is just the bedrock under the ice. The blue is really low. All of anything yellow or brown is above sea level. This is the bedrock of Antarctica as a whole under the ice, and anything yellow or brown is above sea level. The ice is pushing this whole continent down into the mantle. Now here's what we have showing regions below present sea level in blue. So this is a little easier to see it this way. But everything blue is below sea level as it stands right now. Now this is without ice after isostatic rebound. So this is after isostatic rebound. So if you took all of the ice off, Antarctica would raise itself up, and you can see the whole area would just be higher. None of this, I think the blue area over here on the left, only blue is still under the level of the ocean after the ice is removed. Now, this is after the isostatic rebound and a sea level rise of 80 meters, because that's how much the sea level is going to rise after you take the ice off. But the continent is going to rebound and come up. So if it were stayed in the same place it was before, the whole thing would be a lot more blue. But see how much it really comes up. If there's no ice there, this is what it'll look like, and none of that will be underwater except for what you see in blue. And here's a very simple drawing showing how an actual spreading zone would work. That would be the part out in the ocean that pushes the continents apart. Magma comes up here, finds weak spot, and it just keeps coming through. And this forms out, and this side goes this way, and this side goes that way. Another self-explanatory. This comes up, spreads here, here. This is what moves the continents. Another diagram showing every conceivable way that the magma can come up to the surface. So we're getting close to the end of the video here, and if you're still with me, thanks for staying. I know it's a long video, but there's just so much to cover, and I just feel like there's so much I just couldn't cover because of the time. I'm going to go ahead and conclude this with just some real pretty pictures of Antarctica and wind it up from there. So I hope you enjoyed the video. I hope you learned something. If you have any questions or heard anything that I said wrong, be sure and tell me down in the comments there. Or if you have any ideas on your own, be sure and let me know. But I think I got it right. I try to keep it as simple as I can, because I know it's not going to do any good to use a lot of words that nobody understands. And I've never really done a video trying to explain something so big. I think I might have took on a bigger, I should have studied this a lot more, but I just wanted to get this done. But I think I did a fairly good job. You might let me know if you like it or not, whatever. So I'll go ahead and show a couple of more shots of Antarctica. This is actually the southernmost city in the world, and it's at the tip of Argentina. It's called, oh, I forgot, Ushuaia or something. The glacier. There's footprints there. Plenty of penguins. Forgot to mention that a lot of these research places and old ones from the United States, when they abandoned, they just left all their junk there. It looked like a junkyard. It was a crime, environmental crimes, all kinds of toxins all over the place. Oh, there. Notice there's no Kembos. Throwing water in the air. You can see why it doesn't rain there. Okay, well, I hope you enjoyed the video, and everybody just have a great day. Bye.